In November 2022, a small research team bolted a metal box the size of a washing machine onto a floating platform off the coast of China and let seawater flow straight into it with no filter, no purifier, and no desalination plant in sight. What came out the other side was hydrogen gas, clean enough to burn, made directly from ocean water that still had salt, sand, and living microorganisms floating in it. For almost 100 years, every engineer on Earth believed you could not do this without destroying your equipment within days. China just proved them wrong. And by the end of this video, you will understand exactly how a nation with almost no fresh water to spare may have just found a way to turn its 3 million square kilometers of ocean into an endless fuel tank. If you like watching real engineering problems get solved in ways that sound almost impossible, this is the kind of story this channel keeps digging up. So sticking around and subscribing means you will not miss the next one. There's no pressure here, just an open invitation for anyone who gets a little thrill from watching a hard problem get cracked in public, with real data behind it instead of hype. To understand why this matters, you first need to understand why nobody had done it before, and why so many smart people spent decades convinced it was not worth trying. Hydrogen is one of the cleanest fuels on the planet. Burn it, and you get water vapor, nothing else. No carbon, no smoke, no soot drifting into the sky. Car makers, airlines, steel mills, and power plants have all been chasing hydrogen for decades because it could replace oil, coal, and natural gas without wrecking the atmosphere in the process. The problem was never hydrogen itself, and it was never a lack of desire to use it. The problem was making enough of it, cleanly, without spending more energy and money than the fuel was worth. To get hydrogen, you split water into its two building blocks, hydrogen and oxygen, using electricity. This is called electrolysis, and you can think of it like using a tiny lightning bolt to pry apart two dance partners who are holding hands very tightly. Force enough current through the water, and the bond breaks apart, releasing hydrogen gas from one side of the machine and oxygen from the other. Do that at scale, using clean electricity from wind turbines or solar panels instead of a coal plant, and you get what the energy industry calls green hydrogen. On paper, it sounds almost too simple. In practice, it turned into one of the most stubborn engineering puzzles of the last 50 years. This is not a brand new dream either. Engineers have been chasing large-scale hydrogen power since at least the 1970s, when the first global oil shocks sent countries scrambling for any alternative fuel that did not depend on a handful of oil-producing nations. Japan poured billions into what it openly called a hydrogen society decades ago, betting on fuel cell cars and hydrogen-powered homes. Germany and the United States funded their own waves of hydrogen research in the 1990s and 2000s. Almost every one of those pushes eventually slowed down or stalled out, not because the chemistry failed, but because producing hydrogen cleanly and cheaply, at a scale that actually mattered, kept turning out to be far harder and far more expensive than anyone had originally hoped. Here is the catch that quietly derailed the entire industry. Every electrolysis machine ever built needed almost perfectly clean, pure water to work properly. Feed it seawater instead, and disaster follows fast, often within days rather than years. Salt ions attack the metal electrodes inside the machine like a slow, invisible acid, corroding them until they crumble and stop conducting electricity the way they should. Magnesium and calcium dissolved in seawater form hard mineral crusts on the equipment, choking it the way clogged arteries choke a heart, slowly cutting off flow until the whole system seizes up. Tiny living organisms, algae, and floating particles clog the delicate membranes inside the machine, the same way hair and grease eventually clog a kitchen drain. Engineers who studied ocean water found it holds more than 90 different dissolved elements and compounds, a chemical soup far messier and more hostile than the pure, filtered water any commercial electrolysis machine was ever designed to touch. So for decades, the entire green hydrogen industry made an uneasy peace with an expensive workaround. If you wanted to use seawater as your raw material, you had to desalinate it first, stripping out the salt and impurities in a completely separate plant before the water was even allowed anywhere near the electrolysis machine. That extra desalination step ate up huge amounts of energy on its own, added enormous upfront cost, and needed its own dedicated infrastructure just to prepare water for a second machine that was supposed to be making clean fuel in the first place. It was, in effect, like building an entire water treatment plant, just so you could justify building a power plant next door to it, doubling the complexity and the price tag before you had produced a single unit of usable fuel. China had extra, very specific reasons to want a way around this problem, beyond simple curiosity. The country has enormous ambitions for offshore wind power, with massive turbine farms rising directly out of the ocean along thousands of kilometers of coastline, from the Bohai Sea in the north down past Fujian and Guangdong in the south. But most of that wind energy gets generated far from the freshwater sources you would normally need to run a traditional onshore hydrogen plant. building pipelines to carry fresh water dozens of kilometers out to sea, or sending barges back and forth to ferry it in, would have made offshore green hydrogen brutally, perhaps fatally, expensive before it ever got off the ground. Meanwhile, the ocean itself was sitting right there beneath every single turbine, an almost limitless supply of raw material that almost no equipment on Earth could touch without slowly destroying itself. So the real question hanging over the entire industry was blunt. Could anyone actually build a machine that just did not care about salt at all? One that could shrug off the ocean's chemistry instead of fighting it? That question sat unsolved for years until a team led by Xie Heping, an academician with the Chinese Academy of Engineering and a researcher based at Shenzhen University, decided to stop trying to clean the water before it entered the machine, and instead built a machine that simply never let the dirty parts of seawater get inside at all. The idea, published in the science journal Nature on November 30th, 2022, was almost sneaky in its simplicity once you see the diagram. And once you understand how it works, you will probably wonder, like plenty of engineers did, why nobody had tried it quite this way before. Picture a covered swimming pool on a cold morning. Water vapor rises off the surface of the pool and fogs up the glass roof above it, leaving a thin film of moisture on the underside of the glass. Now notice something important about that fog clinging to the glass. It is pure water, essentially distilled. All the chlorine, all the dissolved minerals, all the skin oils and debris that made the pool water anything other than plain H2O stayed behind down in the pool itself. Only the water molecules light enough to evaporate made the trip upward through the air, leaving every bit of the messy stuff behind in the water below. That everyday bit of physics is essentially the trick Xie's team borrowed and engineered into a working machine. Instead of pumping raw seawater directly into the electrolysis chamber the way older designs tried and failed to do, they built a barrier called a hydrophobic membrane, a thin, specially engineered material that repels liquid water outright, but happily lets water vapor drift straight through it. Think of it like a raincoat that keeps rain out but still lets your skin breathe and sweat evaporate away underneath it. On one side of this membrane sits the open ocean, churning, salty, and full of life. On the other side sits the actual electrolysis chamber, sealed off and pristine, where the real chemistry happens. Here is the process broken down into simple, ordered steps, so you can picture exactly what happens inside that metal box. First, seawater touches the outside surface of the membrane, but because the membrane is hydrophobic, the liquid water itself cannot physically force its way through the material. Second, water molecules on that outer surface naturally evaporate, the same way puddles slowly dry up and disappear off a warm sidewalk after rain. Third, only that pure water vapor, invisible and weightless, slips through microscopic pathways woven into the membrane, crossing over into the clean, sealed side of the machine. Fourth, the salt, the dissolved minerals, the microorganisms, and every other troublemaker floating in the seawater are left stranded outside on the ocean side, never once touching the delicate metal electrodes waiting inside. Fifth, on that clean interior side, standard, well-understood electrolysis takes over, using electricity to split those newly arrived, perfectly pure water molecules into hydrogen gas and oxygen gas, exactly the way a laboratory machine running on distilled water would. There is one more piece worth understanding, because it explains why this design survives conditions that would wreck older machines. The electrodes sitting inside the sealed, clean chamber, the parts actually doing the work of splitting water apart, are coated with special catalyst materials designed to speed up the reaction without wearing away too quickly. In older seawater electrolysis attempts, these same electrodes were the first thing to fail, pitted and eaten away by chloride ions within days. The way a nail left sitting in a saltwater puddle rusts far faster than one left sitting in a glass of tap water. Because Xie's design never lets liquid seawater anywhere near those electrodes in the first place, the corrosion problem that killed earlier attempts simply never gets the chance to start. It is less a fix for corrosion than a way of designing the entire threat out of the system from the very beginning. In effect, the machine builds its own private desalination step directly into its outer skin for free, using nothing but the natural physics of evaporation that happens on every lake, sea, and rain puddle on the planet every single day. There is no separate purification plant bolted onto the front of the system, no extra energy, hungry filtering stage, draining power before the real chemistry even begins. The ocean does the sorting on its own, quietly and continuously, exactly the way it always has whenever water evaporates off any body of water anywhere on Earth. Simple, almost embarrassingly so, once someone actually sits down and tries it. So, did an idea this elegant on paper actually survive real violent ocean conditions? Or did it only work inside the calm, forgiving walls of a laboratory tank? The team did not stop at a laboratory demonstration, and this is where the story moves from clever theory into hard, measurable engineering, and where the specific numbers start to matter. The system was carried out to open water and tested at the Xinghua Bay offshore wind farm in Fujian Province on China's southeastern coast, mounted on a purpose-built floating platform named Dongfu No. 1. This platform was jointly developed by Xie Heping's research group and Dongfang Electric Corporation, a major state-owned power equipment manufacturer headquartered in Sichuan Province and one of the largest builders of power generation machinery anywhere in the world, the kind of company that normally builds turbines the size of apartment buildings rather than experimental prototypes. The test results were independently verified by a panel of experts from the Chinese Academy of Engineering, the same national body Xie Heping belongs to, which matters because it means the numbers were checked by outside specialists, rather than simply announced by the company that built the equipment grading its own homework. According to the published data, the pilot system ran at a scale of about 1.2 normal cubic meters of hydrogen per hour, powered in part by a 10 megawatt offshore wind turbine paired with a 28 kilowatt energy storage unit designed to smooth out the natural, unpredictable ups and downs of wind power blowing across open ocean. The platform kept running continuously for more than 240 straight hours, all while facing force 8 winds, waves nearly a meter high, and at least one full rainstorm rolling through, conditions that would make most delicate laboratory equipment fail within minutes, rather than survive for over a week. Despite all of that, the hydrogen it produced came out at a purity above 99.9%, using roughly 5 kilowatt hours of electricity for every normal cubic meter of hydrogen generated, numbers that researchers say land squarely in the same range as electrolysis machines running comfortably indoors on pure, filtered laboratory water. In March 2023, China's Ministry of Science and Technology named the breakthrough one of the country's top 10 scientific advances of the entire previous year, a formal government recognition that placed it in the same conversation as the nation's biggest achievements in space exploration and advanced material science that same year. Xie Heping himself described the milestone in fairly plain terms, saying the team had successfully combined offshore renewable energy with desalination-free seawater electrolysis under real complex ocean conditions, and that the next goal was building an even more efficient system that could resist interference and be scaled up through partnerships with industrial companies around the world. That is not the cautious language of a team happy to keep an experiment safely indoors. That is the language of a team already sketching out factories, supply chains, and coastlines. Put those numbers next to the scale of other hydrogen pilot projects happening around the same period, and the achievement looks even sharper. Several onshore green hydrogen pilot plants built around the world in the early 2020s, running on ordinary purified freshwater, reported similar energy consumption figures in that same 4 to 6 kilowatt hour per cubic meter range, meaning the Fujian platform, working with unfiltered ocean water in the middle of a storm, was already keeping pace with plants that had every advantage of calm, controlled, land-based conditions. That is not a small technical footnote. It is close to the entire point of the experiment. Proof that going straight to messy, complicated seawater does not have to mean giving up serious efficiency to get there. But surviving one storm off the coast of Fujian is one thing. Does that really mean this idea can scale into something the rest of the world can actually use? Zoom out, and the potential here stretches far past a single platform bobbing in Xinghua Bay. Roughly 70% of the Earth's surface is covered in ocean, an essentially limitless reservoir of raw material that most of the world's energy industry has never been able to economically touch, simply because nobody could process it cheaply. Pair a technology like this one with the offshore wind farms that countries all over the world are already racing to build along their coastlines, and suddenly those wind turbines stop being simple electricity generators, sending power down a cable to shore. They start becoming floating fuel factories in their own right, manufacturing hydrogen directly out on the open water and shipping it back to land as a storable, transportable energy source, instead of raw electricity that has to be used the instant it is generated or lost forever. That distinction matters far more than it might sound like at first. Electricity from wind and solar is famously hard to store in large quantities for long periods, which is exactly why a single cloudy, windless week can still strain or even crash a renewable heavy power grid. Hydrogen solves that storage problem in a fundamentally different way. It can be compressed into tanks, shipped across oceans in containers, or piped through infrastructure, much like natural gas already is, holding onto that renewable energy for weeks or months until the exact moment it is actually needed, whether that moment is powering a steel furnace, fueling a cargo ship crossing the Pacific, or running a hydrogen fuel cell truck hauling freight across a continent. A technology that lets you manufacture hydrogen directly from seawater without an expensive freshwater supply chain trailing behind it removes one of the single biggest cost barriers standing between offshore wind power and a genuine functioning global hydrogen economy. For China specifically, this breakthrough lands at a very deliberate strategic sweet spot. The country has poured enormous investment into becoming the world's largest builder of offshore wind capacity, with entire coastal provinces competing to host the next generation of turbine farms. It has separately set ambitious national goals around hydrogen as a clean fuel for heavy industry and transport, sectors like steelmaking, cement production, and international shipping that are notoriously difficult, sometimes close to impossible, to run on batteries alone because of how much continuous power they demand. A technology that connects those two ambitions directly together, letting offshore wind turbines produce hydrogen fuel without needing fresh water piped or shipped out to sea, plays straight into a long-term national energy strategy that has been quietly building for well over a decade. Other nations chasing the same green hydrogen dream, including several across Europe, along with Japan, South Korea, and Australia, are watching this specific branch of seawater electrolysis research very closely, because whoever manages to solve it cheaply and reliably first gains a genuine head start in an industry many governments already consider the next major global energy frontier, on the same scale as oil was in the 20th century. Shipping giants are already experimenting with hydrogen and ammonia-powered cargo vessels. Steel producers in Europe are testing hydrogen-based furnaces that could someday replace coal. Every one of those experiments needs a cheap, reliable, large-scale source of hydrogen to actually succeed at global scale, and right now, that piece of the puzzle is still the most expensive and most unsolved part of the entire chain. Aviation adds one more layer to why this matters so much. Airlines cannot easily run jet engines on batteries because batteries are simply too heavy per unit of energy to ever get a fully loaded plane off the ground economically. Hydrogen, or fuels manufactured using hydrogen as a building block, are among the few realistic paths anyone has proposed for cutting emissions from long-haul flights over the next few decades. International shipping faces the exact same weight and range problem, which is part of why the International Maritime Organization has been pushing member countries toward cleaner fuel standards for ocean-going vessels. Every one of those industries is quietly waiting on the same missing ingredient, an abundant, affordable source of clean hydrogen and a technology that can manufacture it directly from the ocean. Right next to where ships already sail and wind turbines already spin, sits closer to solving that shortage than almost anything else currently being tested. So where, realistically, does a technology this promising still run into trouble on the road ahead? None of this means the technology is finished, proven at full scale, or ready to power entire nations tomorrow. And it is worth being completely honest about that, rather than overselling a genuinely impressive pilot project. The Xinghua Bay platform proved the underlying concept works reliably under real ocean conditions, producing roughly enough hydrogen per hour to fill a single large delivery truck's tank, which is a meaningful proof of concept, but still nowhere near the industrial scale that would be needed to meaningfully dent an entire country's fuel demand. Scaling any chemical process up from a research platform the size of a shipping container to a full commercial plant covering acres of ocean tends to introduce brand new problems that never show up at smaller sizes, from material fatigue building up slowly over years of constant saltwater exposure, to the sheer manufacturing cost of producing specialized membranes by the square kilometer instead of the square meter. There are also open, unresolved questions about long-term durability that a 10-day storm test cannot fully answer. The 240-hour test proved the system can survive one real violent storm without failing, but commercial power plants are generally expected to run reliably for decades, not 10 days, and ocean environments are relentless in ways that only reveal themselves slowly. Barnacles and algae tend to colonize any surface left in seawater long enough, a process engineers call biofouling, and it remains an open question exactly how a hydrophobic membrane holds up against months or years of that kind of biological buildup, rather than a single week-long test. Researchers themselves have openly acknowledged that improving the system's resistance to interference and pushing toward true industrial-scale manufacturing remain active, ongoing goals rather than finished achievements, sitting comfortably in the past tense. Cost is another unresolved piece of this puzzle that deserves honest attention. Building specialized hydrophobic membranes, constructing floating offshore-rated platforms, and manufacturing equipment tough enough to survive years at sea is simply not cheap. And until this particular approach is proven at a scale large enough to genuinely compete on price against conventional freshwater-based green hydrogen production on shore, it remains a promising, well-documented pilot project, rather than a wholesale replacement for existing energy infrastructure. There is also the broader question of how quickly the world can build enough offshore wind capacity to feed systems like this one in the first place, since the hydrogen output is only ever as clean and as cheap as the electricity feeding it. None of these are reasons to dismiss the achievement. They are simply the honest, unglamorous distance that still sits between a brilliant pilot platform surviving one storm in Fujian and thousands of similar platforms quietly supplying fuel to ships, factories, and power grids around the world. Healthy skepticism is not the enemy of a good breakthrough. It is usually exactly what separates the ones that last from the ones that quietly disappear once the headlines fade and the harder engineering work begins. Still, strip away every reasonable caveat, and what remains underneath is genuinely remarkable. A research team in China built a machine that lets seawater evaporate naturally through a specially engineered membrane, keeps every bit of the salt and biological grime stranded outside, and uses only the pure vapor that manages to slip through to produce clean, usable hydrogen fuel, all without a single separate desalination plant standing in the way. They proved it survives real ocean storms rather than only calm laboratory tanks, verified the results with independent outside experts rather than their own internal team, and earned formal national recognition as one of the country's top scientific achievements of the entire year. In doing so, they took one of the biggest, most expensive obstacles standing between the open ocean and a workable clean energy economy, and quietly, methodically removed it, one membrane and one storm-tested platform at a time. If engineering breakthroughs like this one catch your attention the way they caught mine while researching it, following along means you will be here for whatever the next one turns out to be. And turning on notifications, make sure you never miss the moment a story like this one actually drops. Now here is a question worth sitting with for a moment before you scroll away. If floating platforms like this one keep scaling up along coastlines around the world over the next decade, do you think ocean-based hydrogen ends up racing ahead of solar panels and battery storage as the true backbone of the clean energy future? Or do you think it settles into a more specialized role, quietly fueling the hardest to electrify industries like shipping and steel while batteries handle everything else? Type your honest answer down in the comments, because that exact debate is precisely where this technology is headed next.